Good morning, everyone. Today, in this class, we are going to look at the one specific wave, which is sound waves. And I know this is going to be Note Day 5, not Day 4. Day 4 Note on interference, we will cover it when I come back next week. Okay? So, now let's start with sound. To refresh your memory, we have to remember that sound is not a transverse wave. So the particle in a sound wave does not move the same way as a particle on a rope. Sound is a longitudinal wave. Okay, so longitudinal wave produced by vibrating objects. Imagine a flat surface moving back and forth inside a speaker. The vibration of the speaker surface results in a compression and rarefaction in the air. So for example, when I speak, my throat vibrates and it compresses the air, and eventually that compression and expansion of the air molecule travel to your ear. Inside your ear, there's a eardrum. And your eardrum will pick up that vibration, and your brain collects your eardrum and they turn its vibration into a signal which you perceive as sound. Now, eardrum, unfortunately, is not a piece of muscle that you can, take advantage of. If you listen to really, really loud music, or if you happens to be very near an explosion, sometimes the air compresses and expands so much, and the vibration is so big that your eardrum can actually burst. Now, luckily, your eardrum is self-repairable in most circumstances. That means if you give it some rest, even if your eardrum bursts, you give it some rest, a few months later, it should repair itself in most circumstances. But if the damage is too great, it could be irreversible. That's why I would strongly suggest when you listen to music, turn the volume to an appropriate level. Some people in class, when they are working on their own work, they listen to music through their headphone. Well, obviously, if I can hear your music all the way from where I'm standing right now, that's way too loud for you because you actually have the earphone in your ear, and I can hear it from like 10 feet away. Okay, so make sure you don't listen to music with like uncontrollably loud noise. Okay, now another thing is if you need a visual representation of what the wave actually look like, you can actually go and visit our class webpage. Our course webpage has been recently updated, and it will actually now show you a lot of information on these waves, a lot of animations on these waves. So for example, if you go to our course webpage, which we are going to right now, and you look at, let's see. Okay, so let's say you go to Physics 11 and you select wave and sound, and scroll to the bottom. You'll now actually see quite a lot of animated GIF. Okay, a lot of these GIF animation. For example, we're talking about sound wave, so well, there we go. Sound wave on the left panel. Oh, it's really hard to stop exactly there. I overshoot it multiple times. There we go. So, ignoring the wave on the right, so those waves on the left are how sound wave propagate. Okay, so on the left hand side, so you look at like these wave in here. So these are sound wave, right? So your eardrum will be on the right, and someone vibrating a surface will be on the left, and the air compresses and expands and it travels to your ear. Okay, so just a reminder. Now, let's go back to the note. Now, it turns out, so in sound, we have to put different kind of classification compared to other type of wave. So in a sound wave, let me get access to this. In a sound wave, high frequency means high pitch. Low frequency is a no pitch sound. Okay, so the frequency of sound high. Okay, so the pitch of sound is determined by its frequency. High frequency means high pitch, which in a music term is called tremble. And low frequency sound is when you have no pitch, and in a frequency term, that's your bass. So tremble, so high frequency sound will sound like this, ah, and low frequency sound will be like ooh, like that. So high pitch and no pitch. Now human ears, on the other hand, cannot actually hear all the frequency. We have limitation on what we can hear. So let's take a minute and watch a YouTube video, which should be on the course webpage on under the Physics 11 and waves, and let's study what is the maximum and minimum audible frequency for human ears. Now, different animal might have a different value, but then, for human, we have a maximum and minimum audible frequency. Okay, so you should pause this video right now and go to the website and listen to the human audible frequency range YouTube clip. Okay, so pause the video right now. Okay, welcome back. So I assume that you already watched the video, which has the audible human frequency. And what we have discovered is that human, generally speaking, can hear somewhere between 20 hertz to 20 kilohertz. Now 20 kilohertz means 20,000 hertz. Okay, and even anything that has higher frequency than 20,000 hertz, we have trouble hearing. And anything lower than 20 hertz and a sound that's really low pitch, we have trouble hearing also. Okay, now, for example, well, in a side note, dogs can hear both lower and higher pitch sound than human. That's why we have dog whistles. So dog whistles produce a sound that is in the 30,000 or the 40,000 kilohertz. So only dogs can actually hear the whistle blowing. Human cannot. Now, and also sometimes, right, if you have dogs, you probably know what I mean. Sometimes your dog will bark at some random locations, and there's like nothing over there. Sometimes you see a dog barking at like the corner of the wall, and there's like nothing at that corner. You're wondering, okay, so what's the dog barking at? Well, it turns out that sometimes in your house, due to various, electrical or mechanical properties, sometimes your house actually produce sound that are in a wavelength or in a frequency that's higher than what human can detect. So you don't hear it. Maybe it's the water going through a pipe, and maybe some electrical current going through a wire, but you cannot hear it because the frequency of that is too high. But the dogs will pick it up. So the dog actually picks up some sound that humans have trouble hearing. So sometimes you think the dog is barking at like, ghosts, but it's actually barking at some mysterious sound that has higher frequency than what we can hear. And then there's reason for it. Or maybe the dog is actually barking at a ghost. Okay? So pick your explanation. On the other hand, talk about cats, right? So cats, on the other hand, cannot hear low frequency sound. Okay? So what does that mean is, now you look at the cat. So the cats can only hear between 60 to 65 kilohertz. That means high frequency sound the cats are really sensitive to. I guess that's why when we talk to cat, we go like, oh, kitty, 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 like that, right? So high frequency sound, the cats are really sensitive to, better than human. But if you look at the low frequency range and compare that to the human's frequency, human can hear as low as 20 hertz. Cats start at 60 hertz. That means if the sound has too low of a frequency, the cats will actually unable to hear it. So that means if you talk to your cat, for example, like, I guess I cannot actually produce a sound that is as low as that frequency, but I can try. If you talk to your cat like this, which has a very low frequency, your cat will completely ignore you. Not because your cat does not love you, because your cat cannot hear you. Okay? Now, I know the sound I just make is probably a lot as low as it should be, but you can use the program again, right? So the video that you just watched, you can go back and listen to what like 40 hertz sound like. Your cat cannot hear that one. Okay? So sometime when you talk to your cat, people usually use higher pitch noise, higher pitch voice to do that. There's a reason, because your cat responds really well to high pitch noise, just not too well to no pitch one. Okay, so fun facts, right? Now moving forward, okay, so that part is good. So we are going to look at speed of sound. Now, last time we looked at speed of other kind of waves, and we determined that, okay, so the higher the density usually means that the wave moves the slower. But sound is not a transverse wave though, right? Sound is a longitudinal wave which works exactly the opposite way. So for a longitudinal wave, like sound wave, for example, the speed of the sound wave is actually dependent on the medium. Now usually, the more dense, the faster the sound wave will travel. So the speed of sound wave in solid beats the speed of sound wave in liquid, which could be water, which beats the speed of sound wave in gas, which is air. So the speed in, for example, steel is faster than the speed in water, which is faster than the speed of sound in the air. Well, then how fast does sound travel in the air? Well, depending on temperature. Because temperature changes the density of air too, right? So sound travels faster when the temperature is higher. So it turns out that at room temperature, sound travels at 344 meters per second at room temperature at sea level. What is room temperature? 20 degrees Celsius. But if the air is really cold that day, like 0 degrees Celsius, then sound only travels at 331 meters per second. Okay? So there's a small difference between that. Now, so once we know that, we can actually get the equation. So people have been measuring how fast sound travel at different type of temperature, and they come up with a trend. The trend is the sound travel faster in warm air compared to cool air. The speed increases by about 0.6 meter per second for every 1 degree Celsius of temperature increasement. Okay, so every time the temperature goes up by 0.6 meter per second, the speed of sound, the temperature goes up by 1 degree Celsius, the speed of sound goes up by 0.6 meter per second. So then we can get the equation. So the speed of sound is 331 meter per second, which is like a base value, plus 0.6 times the temperature of that day. So this T right here is not the period, it's the temperature. Okay? And it's temperature measured in degrees Celsius. Please don't use Fahrenheit. Okay? And now this equation should be on your formula sheet. But I guess if you want to be safe, since we do have a unit, we do have a symbol called period, which also use T in this unit. Make sure there's a different, the difference between this T and the other T. The other T is period, which is measured in second. That's how long the time it takes for the wave to travel one cycle. Whereas this is T as in temperature T, and it is measured in degrees Celsius. Okay, so we're going to go through a few examples. Now, I know that on to the right there's a box for the March number, which we're going to ignore for now. We're going to go through a few examples, and then we're going to come back to that box. Okay, so example, what is the speed of sound in the air at 5 degrees Celsius? Oh, that's easy. Directly application of the equation. So 331 is the base value, 0.6 for every degree Celsius, and now we have 5 degrees Celsius. So that 5 times 0.6 is a 3, so we add 3 to it, 334 meter per second. Okay, so that's an easy one. Now, to the next one. Okay, so a bass guitar produces a 70 Hz sound wave at a room temperature. Okay, wait, at room temperature means at like 20 degrees Celsius. Determine the length of this sound wave. So in order to do this, we actually have to use two equations. So first, we have to find out how fast is the sound wave in this room. which is 331 plus 0.6 times the temperature. Now the temperature is 20 degrees Celsius, so we can put it in here and get the speed of the sound at room temperature. Or most people actually memorize the speed of sound at room temperature, which was the first value we wrote down, 343 meters per second. It was in the last paragraph that we worked on. So if you memorize it, it's okay. You don't have to work it out. Otherwise, work it out this way. Okay. You say, okay, so now I have the speed of the sound wave. What do I do to get the length of the wave? Well, you do remember that for any wave, we learned last class, any wave speed can be calculated by lambda f, the wavelength times the frequency. So the speed of sound is a wave. I mean, sound wave is a wave, right? So therefore, we can say, well, the sound wave is 334 meters per second in terms of speed, and it's equal to lambda multiplied by the frequency, which is 70 hertz. So if you take those two and divide them, you get 4.9 meters as the wavelength. Okay, so in this example, we had to use two different equations. We had to use a speed of sound wave, and then we had to use the wave equation, which was from last day. So now is a very good time to consolidate all these speed equations, because there are now two, but if you remember on day one, we actually had another speed of wave equation. Now let's write them all down. So first, we have distance over time as the first speed equation, and that was learned in kinematics. Now this one, distance that you travel over time, is for everything. Okay, then last two classes, we pick up this equation, which is called the wave equation. This equation has wavelength and frequency. This equation only works for speed of a wave. Today, we pick up another one, which is the speed of sound wave. Now this one works for sound only, in the air only, so 0.6 multiplied by the temperature. So this one is for sound wave only. So if you have a wave traveling on a rope, then you can use the first and the second equation, but you're not allowed to use this third one. So this one is for sound wave only. Okay, so this one is only for sound wave. Now, so that means if you're working on sound wave, there is actually a possibility that you have to use more than one of these equations, because sound wave, of course, satisfies the last equation for sound wave only, the second equation for any wave, and the first equation for anything. But if you have a wave traveling on a rope, a wave traveling on a slinky, a wave traveling, in space, like speed of light, then the only equation you can use is the middle one, because the middle one works for any wave, whereas the speed of sound equation only works for sound. I mean, hence the word speed of sound, right? Okay, so I want to go through another example before we go back. So let's go to the next page to look at another example first. Okay, so this question is asking for two things. A 250 hertz sound wave is 1.42 meters long. Determine the speed of the sound in the air, and also what is the air temperature of that day. Okay, first, 250 hertz is a frequency, 1.42 meter is a wavelength. With frequency and wavelength, we can use the second equation that we wrote down earlier. So this goes with any wave, which is lambda f. So the speed of a wave is lambda f. So we put 1.42 meters and 250 hertz to get, well, the speed of the sound is 355 meters per second in your calculator. Now, so that's part one. That's also one of the question. So now we have to answer part B, which is what is the temperature of that day? Well, okay, so if it involves temperature, then I guess I need the other equation that has temperature on it, right? So speed of sound wave is equal to a base value 331 plus 0.6 times the temperature. So we're looking for the temperature, but we got a wave speed from another method. So we will substitute wave speed in here, which is 355 equals to 331 plus 0.6 T. Solving for T, the temperature of that day. Be careful though, when you solve for this T, make sure the 331 is the first step to go, and then of course subtract 331 by 355 divided by 0.6, and you get the temperature of that day to be 40 degrees Celsius. Pretty hot day. 40 degree Celsius. All right. Now, so we have done a couple of exercises. The exercise that's on the worksheet will be mostly based on these two or three equations. Actually, all three of them. So let's go to the March number box that we skip first, and then you'll get the rest of the class to work on these problems. Okay, so we go back to the last page, which talk about something called March number. So the March number is a number that compares the speed of an object to the speed of sound. Now, we had that makeup because back in the day, if your machine can go faster than the speed of sound, it's such a great accomplishment. So we say, oh, you have reached Mark 1 or Mark 2. Mark 1 means you have reached the speed of sound. Mark 2 means, well, you have reached double the speed of sound. Mark 3 means 3 times the speed of sound, and go on. So it's basically a ratio of the object speed to the speed of sound. And you can calculate from Mach number equals to the speed of the object over the speed of sound. Now, this is not an equation on your formula sheet, but okay, it's kind of obvious. So Mach 1 is 1 time the speed of sound, and so on. Mach 10 will be 10 times the speed of sound. So now, if you have a cruise missile and it's traveling at Mach 0.8, what is the actual speed? Okay, so first of all, so if I have Mach 0.8, so 0.8, so what's the speed of that compared to the speed of sound in room temperature? So we're going to assume that it's room temperature on that day, which is 334 meters per second. So V is multiplying that by 0.8, which is 274.4 meter per second. Okay, so that is how fast the missile is traveling. Okay, so now in terms of the new note, we're going to stop here today, and you have a worksheet. I think the worksheet is actually called, this is day 5. I think it is called worksheet 5 on sound wave. Okay, so look at worksheet number 5. Worksheet number 5, which is on sound wave. So I want you to work on that for the rest of the class. I will post the answer key online, written answer key, so the one that has extra works on it, not just the answer itself. Because those questions look easy, but a lot of time it gets a bit confusing. Particularly because a lot of questions involve echo. Echo means you have something that makes a sound, and the sound travels to an object and come back to you. So if someone makes a sound and it travels to the object and it refracts and come back to you, you have to remember that means the sound wave has actually traveled double the distance between you and the object. So a lot of the question will ask you, okay, so what is the distance between you and the object? And they might give you the time it takes for you to hear the sound wave back. So you have to make sure that you understand this concept, which is the time it takes you to hear your echo in that time, your wave has already traveled 2D, 2 times the distance between you and the object, because your sound wave has to go there, do a reflection, and come back to you. Now, we already look at reflection coming back to you. It has the same speed as the wave going toward it. So it's the same amount of time going there and coming back. But you only hear your echo when the sound comes back to you, right? So you make a sound, the sound has to travel to the object, come back to you. So the time it takes is for the object to go forward and backward. So that means the sound has already traveled double the distance between you and the object. So keep that in mind when you do these questions. A lot of them involve that. Okay, so I'll be back tomorrow. If you have any questions for me, feel free to look for me tomorrow in my room. And have a good weekend.